This is a vector sum, so it's not just going to be a simple arithmetic sum. I'm not just going to add up the numbers. Instead, I'm going to have to do all this business like we've been doing, where I find the x and y components of A, B, and C. I add up the x and y components separately of A, B, and C to get the x and y components for R, and then I do the Pythagorean theorem and the tangent thing to find the magnitude and direction. So really just a few steps. It might seem like there are a bunch of steps, but they're really just a few steps. Find the x and y components of all my vectors, add up all the x components, add up all the y components. If there are z components, do that too, but we won't get to that until later. And then find the magnitude and direction of my new vector r, which is the sum of those x and y components. So sometimes I like to make a table. This might be useful for you too if you like that. My x component, remember if I want to find the x component of a vector, it's a cosine theta. The y component of a vector is a sine theta. So here, my x and y component of A is going to be 2.236 times the cosine of 63.43. And this works out to be equal to 1. And then the y component is 2.236. That's the magnitude times the sine of 63.43. And this turns out to equal 2. I want you to take a moment and just find the x and y components of B and C on your own. I'll give you a minute or two and then I'll jump in there. So find the x and y component of B and the x and y component of C. And then if you finish that, go ahead and find the x and y components of R. Go ahead and find Rx and Ry. If you might need a calculator, try this. Here you get some really round numbers, so just write them off with no decimal places is fine. Just another minute. That's for your values. Bx, what is Bx? It's equal to 3. By is 4, we'll come back to that. Cx, 2, and then Cy is 5. Okay, now we have to be careful here because we want to get our signs correct. And right now we have some negatives on some of these components that we haven't written. So we need to make sure that we know what the signs are for these. And the way we do that, the best way to do that, well, when you get good at this, you'll just be able to look at vector A and be able to tell that vector A is in which quadrant? It's in the quadrant 1, so the x and the y component are both going to be positive. But in the meantime, before you're good at this, or before you're sort of more experienced at this, we'll just sort of sketch them out. So this is vector A. It's in quadrant 1. Vector B is 53 degrees below the positive x-axis. So this is B. Now that means that for vector B, which of the components is going to be negative? The y component. So we need to make sure that we get a negative value there. If you don't get a negative value there, then you're going to get the answer wrong in the end. And then the vector C was 68 degrees above the negative x. So the vector C is right here. That means which component is going to be negative for C? The x direction. So the proper way to record the components of these vectors would be in this way, getting the negatives here for cx and by. Right now, if we want to figure out what rx is and ry is, well, we first want to say, what are we doing to the vector? And in this case, we're just adding up a, b, and c. So rx is going to be ax plus bx plus cx, and that is equal to, well, 1 plus 3 minus 2. That's 4 minus 2, or 2 meters. So that's my x component of r, and then ry is going to be ay plus by plus cy, and then this is 2 minus 4 plus 5. It's negative 2 plus 5, that's 3 meters. So these are our x and y components of r. So remember, several steps. Find the x and y components of all the vectors. We've done that. This is our second step. Add up the x components and the y components to get the x and y component of our new vector. In this case, we're calling it r. And then our final step, this is step number 2. Our final step is to find the magnitude and direction of r. And we do that with our Pythagorean theorem and our tangent function. So here we say this is the square root of 2 squared plus 3 squared, which is 4 plus 9, or square root of 13, which is 3.6. And then the angle is the inverse tan of ry over rx. Remember, we're dealing with a triangle here. This is ry, this is rx, this is our angle theta, and this is the magnitude of r. So we're just doing right angle trigonometry. The inverse tan of ry over rx, that's 56 degrees. We also need to qualify this. It's generally the default that it's above the positive x-axis, but it's always good to clarify that, because as you saw when we gave vectors a, b, and c, it wasn't always the case. And sometimes they were above the negative x-axis, sometimes they were below the positive x-axis. And so you should qualify that as above the positive x. We can also do different things with vectors. Instead of, say, taking the sum, I can take the difference, a minus b minus c, and then go ahead and figure out then what would be rx and ry, and then go on and find out the magnitude of r and the angle theta. So here, instead of adding up ax, bx, and cx, you're doing this operation instead. So try doing this. Don't forget to include those negative signs in the components that we found. Once you find the x and y component, you should be pretty easily able to find the magnitude and direction. Not much less. What's the x component? The x component is 0. That's 1 minus 3 minus a negative 2. That's equal to 0. And then similarly, the y component is 2 minus negative 4 minus 5. That's equal to 1, right? And so my magnitude and direction, well, this is pretty easy, right? Because I only have a y component. So that means my magnitude is the same as that y component, and my angle is Not 0, but it's what? No, it's not undefined. No, it's not negative 45. Oh, okay, let me just draw it. So this is our y component is in this direction, right? And so this is also equal to our vector r. What is the angle for this vector? 90 degrees, yeah. So the angle theta is 90 degrees. If you're uncertain about that, if you just want to check by the same process that we're doing, you can say that the inverse theta is the inverse tan. Oh, that might give you undefined. Does that give you undefined if you put that in your calculator? Okay, well you just have to think about it then. Because our angle can't be undefined. I understand that. But yeah, so our angle here is 90 degrees. Right, from the positive x. Um, 2 plus 4. Oh, yeah, just kidding, is that what you said? Yeah, okay. Yeah, because this becomes positive. 6 minus 5 equals 1. All right, can I do one more example? Okay, we'll do one more. I have a little video I'm going to show you. This is from a French cartoon. Some cardinal directions in our vectors, because you will need to know how to deal with cardinal directions, north, south, east, and west. Those of you in the lab, you've dealt with this already in the vector scavenger hunt, but you'll probably see it on your exam too. So let's just show you how we deal with these cardinal directions. Remember your compass rose, north, south, west, and east. All right, so this guy, when he travels, his we can trace out his vectors in a couple of ways. I can say that I'm just going to sort of ascribe some distances to these particular vectors, and I'll draw them out as vectors. So he goes 5 meters south. I'm going to call that negative because it's down. South is negative. And then he goes, say, 20 meters east, and then he goes 20 meters south. It's right here. And that's going to be negative again. And then 10 meters east. That's going to be positive because it's to the right. And then 5 meters north to get into the girl's house. He eventually does make it to the birthday party, by the way. He goes to all these various adventures, but then he makes it to her birthday party. So what I want to do is I want to add up all these vectors, and I'm going to figure out a resultant vector that will take me from here all the way to here. Remember our graphical method, which you also need to know for the exam in a few weeks, where I sketch out the vectors, and then the sum of all these individual blue vectors is the same as this red vector. Okay? So I think about starting here and ending here at my beginning and ending points. I can sketch out the x and y components. I made a little table on the next page. My 5 meter south vector, it has an x component of 0, a y component of negative 5. My 20 meter east has positive 20 and 0. 20 meters south is 0 and minus 20. 10 meters east was plus 10 and 0, and 5 meters north is 0 and plus 5. And then I do my, the third or the second step. After I find the x and y components, I add them all up. So this is 30, and then this is minus 20. So if we look back at that sketch of the vectors, I'm going to go back up. If we look at this sketch of the vectors, this has a y component of minus 20, and it has an x component of 30. And so that jives with what I know it just as I sketch this out. But those components do look reasonable in the way that I've drawn it. Then I can do my business with Pythagorean theorem. I do the square root of 30 squared plus negative 20 squared. Notice that this goes away when I square it. So often a mistake that students will make is that they'll say 30 squared minus 20 squared is 400. So they say 900 minus 400. But that's not correct, because your negative is going to go away when you square that number. Negative 20 times negative 20 is positive 400. And so that is equal to 36 meters. And then to find my angle, theta, that's going to be the inverse tan of 20 over 30. Or if you want to include that negative, that's okay. And depending on your calculator and how savvy it is, it might actually give you the right angle. But if you just sort of have, I don't know, a calculator that's run-of-the-mill kind of calculator, you don't want to practice with this and sort of see what your calculator does. But if you just sort of have, a basic TI, just leave the sign out and then think about where the angle is oriented from. So if I do this 20 over 30, I get 34 degrees. If you do it and putting in the negative, you might get minus 34 degrees. Or you might get, what is it? I'm sorry, what? 326 degrees. So those are all the same, but I can draw my vector. I know that it is in this quadrant because it has a negative y component and a positive x component. So this is my angle that I'm looking at. Notice this is either 34 below the positive x, it is minus 34 degrees from the positive x, and here my negative denotes the below. Or I could say, what was it, 326? Is that right? Or I could say 326 degrees from the positive x, or above the positive x. And what that would be, that angle would be this angle, 326 degrees. All right, but since I'm in cardinal directions, really the way I want to express this is I would say that it is 34 degrees south of, what is that, east. 34 degrees south of east. Let me show you how to express these cardinal directions. I'm going to go up. You should have some space up top. So when I have these cardinal directions, north, south, west, and east, let's say that I have an angle right here. Let's say that it's 40 degrees. This would be 40 degrees north of east. All right, this is east. This is going north of east. Over here, how would I express this angle? South of west, right? South of west. Over here, I would express this as north of west. And then over here, I would express this as, what would this be? South of east. I know you geomatics guys, you might do this differently. I'm not sure how y'all deal with cardinal directions, but in this class, this is how we'll deal with it. We'll always express it as either north or south of our horizontal axis. All right. Okay, any questions about vectors? Let's do a few clicker questions. We had a few of the concept test questions left over. I don't remember which one we left off on, though. If y'all could let me know. Anybody know where we left off? Did we do them at all? Yeah. We haven't started them at all? Okay. There aren't that many on vectors, so let's go through them. If vectors are given such that a plus b equals 0, what can you say about the magnitude and direction of vectors a and b? In this, when it's bolded, that means the vector sum. So this, we're just assuming this is the vector sum. So vector sum of a and b is equal to 0. So what can you say about the magnitude and direction of those vectors? All right, we'll go about 8 more seconds. Stopping at 50. Stopping at 50. Okay, D, same magnitude, but they must be in the opposite direction. In order to get a vector sum that adds up equal to 0, I must have one vector in one direction and one equal but opposite vector. All right, say for example, this would be plus 2, this would be minus 2. When I add those two up, I get 0 as the sum. Given that A plus B equals C, that is the vector sum of A and B is equal to the vector C, and also that the magnitude of A squared plus the magnitude of B squared is equal to the magnitude of C squared, how are these two vectors oriented with respect to one another? Perpendicular, parallel, same or opposite directions, 45 degrees, or at any angle. We'll stop at 55. Remember to ask your neighbor if you like. Some of you still have the wrong answer on this, but ask your neighbor if you like. Or ask your neighbor anyway. Or just tell your neighbor what you put. Has everybody told their neighbor what you put? Brennan, what did you put? Alright, I'm going to stop at 112. Okay, good. Why are they perpendicular to one another? Why is it A? They're at a 90-degree angle, and I know that because of this relationship, which should stand out to you. This is the what? This is the Pythagorean theorem. That is only true when they're at 90 degrees to one another, so that if I have the vector A here, the vector B here, and the vector C here, this relationship is only true when this angle is equal to 90 degrees. It's only true for a right triangle. All right, given that A plus B equals C, that is the vector sum, A plus B equals C, and then also the sum of their magnitudes is equal to C, how are A and B oriented with respect to each other? Vector sum and the sum of their magnitudes are equal to one another. How are those two vectors oriented? Remember, ask your neighbor what they put and tell them what you put. All right, I'm going to stop at 1 minute. Stopping at 1 minute, just 5 more seconds. Okay, B is right. Let me show you. So the vector sum A plus B equals C. Let's say that this is A, the vector A. This is the vector B. The vector sum would be this vector, if they're oriented in that way, right? However, this is also true. Let's say that A has a magnitude equal to 2, B has a magnitude equal to 3, then that would mean if they're oriented in this direction, that C has a magnitude equal to 5, but only if they're oriented in that direction. So for example, if instead I had A here, B here, then C, this would not equal 5. It would be some value less than 5, in fact. So it turns out that here, the maximum sum that I can get for two vectors is when they're parallel and in the same direction. So it is B is the right answer. All right, if each component of a vector is double, what happens to the angle of that vector? Double the x component, I double the y component, what happens to the angle? Back on your geometry, y'all doing pretty well on this, but ask your neighbor and tell your neighbor what you put. All right, we'll stop at 1 minute. 1 minute. All right, 88%. C is right, it does not change. So if I have two vectors that are like this, if I double one and double the other, like that, I still get the same angle. I think these are called similar triangles, am I right about that? So these are called similar triangles, they have the same angle. So we'll say 88% is good enough. So, knock knock. Interrupting pirate. Arr! It's an interrupting pirate. That was a good joke. Okay, does not change. A certain vector has x and y components that are equal in magnitude. Which of the following is a possible angle for this vector? If the x and y components are equal in magnitude, which of these is a possible angle for that vector? All right, we're going to stop at 45. Okay, let's see. A lot of you put B. The right answer is E. What was B? 180? Okay, let's draw our coordinate system. Our coordinate system looks like this. If I have equal x and y components, it means my x component is here, my y component is here, they're equal. That means that this is an equilateral right triangle, so that this angle has to be 45 degrees. If both x and y components are the same in magnitude, then the angle has to be 45 degrees. Or it can also be some other angles. What would be the other angles it could be? Okay, it could be negative 45. What I'm getting at is it could be in any quadrant. Like I could have a negative x component and a negative y component, putting it in this quadrant. So it could be 45. It could be 135. Y'all can't see that, can you? 135. Or it could be down in this quadrant, which would be, what's that? 225. Or it could be down in this quadrant, which would be 315, that's right, are you sure? Yes, you're right, 315 degrees. So it can be in any one of those quadrants, depending upon whether the components are positive or negative. All right? If I have a positive x, negative y, which quadrant am I in? I'm in 4. If I have a negative x, negative y, which quadrant? Yeah, I'm in 3. If I have a negative x, positive y? I'm in 2. And then positive, positive is in 1. It's good to know your quadrants. We're dealing with vectors. You're adding vectors of length 20 and 40 units, which is the only possible resultant magnitude that you can obtain. So only one of these is a plausible answer or a possible answer. Which is it? That's a dirty bill. That's a dirty because of this thing. I know, and Laura, awesome. Okay, we're going to stop at 50 seconds. 50. We had a very similar question to this earlier, so if you're thinking that it looks familiar, it is. I'm still going to stop at 50 though. Okay, awesome. C is right. Okay, so these two vectors, you can have a maximum and a minimum. The maximum is when they're in the same direction. That would be 60 units. The minimum is when they're in opposite directions. That would be 20 units, right? 40 minus 20 would give you 20. So it has to be somewhere between 60 and 20. So C is the only answer. You can't get any of these other options with these two vectors. Those just are impossible to get when you do the vector sum of these. This joke is kind of crude, but it came from my son, so, you know, middle school boys. Embrace yourself. You ready? Knock knock. Smell knock. Y'all don't get it. Seriously? You can ask Juana after she'll explain it to you. Okay. Come back to this. We're moving into the projectile motion. Feel like you have a pretty good grasp on vectors. But if you go down to the homework, there are some, well, I take that back. Are there vector problems in the homework? Yeah, there's a vector problem number 2. It's a good one. It's dealing with, there's a good one for graphical analysis number 3. Another one, graphical analysis number 4. Number 5 also. So you have some good practice problems. Also look back at the old test so you can find some other practice problems. All right. Let's look at two-dimensional motion or projectile motion. Two-dimensional motion is just, it's going to be a lot like what we did in the previous chapter for kinematics. So if you're still sort of struggling a little bit on kinematics, that's okay, because we're going to pick it up in this chapter, and you'll master it in this chapter. The good news is that this is sort of the end of our kinematics. We'll sort of see kinematics throughout the semester and throughout next semester too, but not in the same detail as we'll see it here. So this is sort of like our last hoorah for kinematics. We'll see it a little bit along the way, but not in as much detail. All right, so it is two-dimensional motion. We're just going to deal in the x and y motion, x and y directions. We have some basic guiding principles or some basic rules in each of those. In the horizontal direction, the acceleration will equal to 0, and so therefore our velocity is constant. In particular, we're looking at the velocity in the x direction. And then in the vertical direction, our acceleration will be -10. And so as a result, we're just going to treat this like a free fall problem. I'm going to write our equations. Remember, we had two kinematics equations. We had that y is equal to v0 times t plus 1/2 a t squared. And then we also had v equals v0 plus a times t. Remember, these were our two kinematics equations. You'll have to derive them for the test. We're going to use these same equations, except we're going to break them into our x and y components. So using these rules, we can sort of rewrite them. We're not really rewriting them, we're just getting rid of some parts of them. And we're going to distinguish between the x and the y. So I'm going to do that by putting subscripts on the v's and the a's. Similarly, up here I'll put a v0y and an ay. So these equations look just like the ones that we had before. In the x direction, they're going to look a little bit different. I'll have x equals vx times t, and really that's it, because I also have vx equals v0x plus axt. But this goes away because ax is equal to 0. And similarly, actually, I have another term here, 1/2 axt squared. But it goes away too because ax, the acceleration in the x direction, is equal to 0. So all this is saying is that the velocity is constant. So that's not really an equation so much as just we're saying that our velocity remains constant, so I'll just get rid of that. So we really just have 1, 2, 3 equations, but they're really just 2. It's just in our x and y directions, they're stated a little bit differently. Okay? So we're going to be using these as we go through projectile motion problems. Also, this is just a quirky fact that will become important later. An angle of, angle will give you maximum range for projectile motion. You probably know this sort of intuitively. In fact, my pastor, he likes to say, because he used to coach soccer, he says that even a 4-year-old knows how to work projectile motion. They do it in their head before they kick the ball. They know certain things will give you more range and other things will give you less range. Did y'all know that you ever play soccer or anything, like when you were 4? Some of you have. But you know how to work projectile motion problems. And you can do it in your head and you can do it in real time. You didn't know you could do that, did you? Yes, you can. So an angle, what angle will give you maximum range? 45 degrees, right. Now we'll see why that is later. In short, it's because it gives you maximum hang time with maximum speed. It maximizes both the time that your projectile is in the air and also it maximizes the x velocity. And both of those combined give you a maximum range. So an angle of 45 degrees gives maximum range. You ever try to spray somebody with a water hose and they run away from you? Right? If they run away from you, spraying like this, what do you do if they run away from you? You go at a bigger angle and then it goes farther. But at some point, you go too high of an angle and it starts to come back towards you again. So there is a place where we get maximum range. You can try that and you'll find that it is 45 degrees. So if you plot out our motion looks like this. I start here and it travels through a parabolic path. It is a parabola. And we have a couple things that happen. So first of all, this is our V0. A couple things I want you to notice is that V0x remains constant. So Vx is constant. And then Vy should look really familiar to you. Vy is initially big, it gets smaller, it goes to 0, and then it gets bigger in the negative direction again. So this was just like when we had something, we throw it up in the air and it comes down again. It goes up, it stops, and then it comes back down again. Listen, we'll still see some qualitative graphs on this stuff like we had on the previous test. I'll ask you to sketch out the graphs of the motion. So if I were to plot out Vx versus t, you go ahead and try that, and then also plot out Vy versus t. Think about what those would look like and sketch out the graph of Vx versus t and Vy versus t. What's going to happen to them? Make sure that you begin at the beginning and end at the end. So sketch out Vx and Vy. And then similarly, if you get that quickly, go ahead and do what does x versus t look like, and what does y versus t look like. Vx is going to be curved or straight? It's going to be a straight line, a linear line. How's it going to be? Positive slope, negative slope, or zero slope? Zero slope. Vx versus t is going to look like that, because Vx is always constant. And in this case, because it's traveling to the right, it's also positive. So we'll draw it as positive. The slope of this is 0. What is the slope of the V versus t graph here? Acceleration, right. And the acceleration in the x direction is 0. So we would expect the slope of this equal to 0. And the Vy versus t, straight line or curved line? Is it going to have a slope positive, negative, or 0? Negative. What is going to be the value of that slope actually? Negative 10, because the slope is the acceleration. And so we're going to start up here where it has a big positive velocity, go down, it comes to the top where it stops, and then keep going where it increases in the negative direction. And by the way, if we start up here at positive 10, we're going to end down here at negative 10. It'll return, if it returns to the same position, it'll have the same speed. All right. My x versus t, straight or curved? Straight or curved? The x position versus time. It's going to be a straight line. It'll have a positive, negative, or zero slope. It's going to have a positive slope. It'll look like that. Remember, the slope of this line is represented by the value of this line. So this slope is always the same, so this value is always the same. And then here, this one's a little more complicated. I'm going to start out with a big positive slope. That slope will decrease to 0, and then it will increase to a big negative slope. So this graph is going to look like that. Just like the picture that we had before as a parabola. Okay? Be able to sketch and describe those graphs related to projectile motion. Let's watch this video. We're not going to have time to go through this, but we will next time. But let's just try and watch the video. Let me see how long it is before I tell you to put stuff away. You know what? We'll just watch the video and then I'll let you go. So you can go ahead and put your business away.